please join first. Can you see the screen? Yeah, I'll share the screen now. Hope you can see the screen. So today morning, where did we stop? Do you remember what we were discussing in the morning? Anyone? We were finding solutions for non-homogeneous recurrence relations, isn't it? And we had discussed one case, case one. And what was that case one? What was case one? For non-homogeneous recurrence relation, there are different cases. The first case that we were looking was, what do you remember? We will be studying around three cases. And the first case, three important cases. And the first case that we were looking at was for non-homogeneous solution. What was the first case? Do you remember? What is case one? Anyone please give the answer? Or type in the chat box. Very good, Agish. F of n is equal to a constant. When the function on the right hand side is a constant. When there is nothing on the right hand side, it is zero. And so we call it as a homogeneous recurrence relation. And we had studied how to solve homogeneous recurrence relation. And when there is f of n on the right hand side, we have to find the particular solution also. Apart from homogeneous, we have to find the particular solution also. So the first case was when f of n is a constant. So we had done one example for f of n is a constant and the method to solve it. Okay, and the steps we had written earlier. So these were the steps to find the particular solution. You have to first put a of n is equal to p, and if it fails, then you put a of n is equal to np in the given equation, and if it again fails, you put a of n is equal to n square p, and so on until you get a value of p. And finally, you will get the particular solution. And then you have to solve homogeneous solution also separately. And when we add these two solutions, homogeneous solution and particular solution, we get the general solution. Okay, so now let us move on to the next case for solving homogeneous, non-homogeneous recurrence relation. Case 2. Now we are solving non-homogeneous recurrence relation. And the case 2 is, you have a polynomial on the right hand side. When there is a polynomial, when f of n is a polynomial. Okay, when f of n is a polynomial. When f of n is a polynomial. That is, we have c0 plus c1 into an example, c2 into an minus 2 is equal to, say, n plus 2n or n square plus 2n plus 2. So there is a polynomial on the right hand side. So earlier we saw that it was a constant one. Our case one was the f of n, this function f of n was a constant. 1 or 2 or 3, any number. Now here we find that there is a polynomial on the right hand side. So f of n is equal to a polynomial. So how can we solve if a polynomial appears on the right hand side of the homogeneous non-homogeneous equation? Okay, so let us see how to solve it. Question. Now, through this question, we can find out how to solve this. Solve the recurrence relation. Solve the recurrence relation. A n plus 1 minus a n is equal to 2n plus 3. So looking at this, we find that all we have moved all n terms to the left hand side, and what is remaining on the right hand side is a polynomial, isn't it? What is remaining on the right hand side is a polynomial, and looking at the power of n, we say that it is of degree 1, isn't it? So when a polynomial appears on the right hand side, what we have to do is the particular solution. When a polynomial appears on RHS, then the particular solution, homogeneous solution, is obtained by equating this to 0 as we had done earlier. But we are kind of bothered now about the particular solution only. So the particular solution is given by an of particular is equal to d0 plus d1n plus d2n square plus etc. Now if the degree is 1, here we find that the degree is 1, so we take only this much part of the equation to solve, to find the particular solution. If it was degree 2, that is 2n square plus 3n plus 6. So here the degree is 2. If the degree is 2, then you have to take the first 3 terms. If the degree is 3, then you have to take 4 terms. Till the degree 4 you have to take. So this is how we are going to solve it. And for then this d0, d1, etc. are constants. We have to find out the values of d0, d1, d2, etc. and substitute in this equation. Just like for homogeneous solution, we found out the value of C1, C2, etc. and substituted in an of homogeneous equation. Likewise, we have to find the values of d0, d1, the coefficients d0, d1, etc. and substitute in this equation to get the particular solution. So if a polynomial appears here, we have to use this formula, look at the degree and choose the number of terms to be included in the particular solution. So let us see how to solve this example. That is an plus 1 minus an is equal to 2n plus 3. And here given n is greater than or equal to 0 and a0 is equal, the initial conditions are also given. This is a question. Solve this recurrence relation. So looking at the right hand side, we find that it is a polynomial of degree 1. Okay, so the general solution is an is equal to an homogeneous solution plus an particular solution. When we solve this left hand side, you get homogeneous solution. When we solve the right hand side, we get the particular solution. When we add these two, we get the general solution. Okay, so what we want to find is the general solution. For that, we have to find the homogeneous solution and the particular solution. So homogeneous solution, as you know, you just equate this left hand side to 0. It becomes a homogeneous recurrence relation and find and solve it. Okay, so let us now find the step 1, homogeneous solution. Find homogeneous solution. Find homogeneous solution. So to find homogeneous solution, what we do is we equate this part to 0. That is an plus 1 minus an is equal to 0. Okay, now to find we are going to use characteristic root method and find the root. So instead of a, you write r and bring this suffix to its power minus again r raised to n is equal to 0. Next, divide by the lowest power r raised to n. Divide the equation by the lowest power, that is r raised to n. You get what? R raised to n plus 1 by r raised to n. What is r raised to n plus 1 by r raised to n? It is equal to r raised to n plus 1 minus n. You get r, isn't it? So this is r minus r raised to n by r raised to n is 1 is equal to 0, or r is equal to 1, isn't it? So I have found out the roots of the homogeneous solution, that is r is equal to 1. I have a single real root, isn't it? I have a single real root. So what is the homogeneous solution? If there is only one root, if there is a single real root, then the homogeneous solution an of h. Look at the, if, we had studied many cases, single real root, two distinct roots, then two same roots, etc. We have formulas for different cases when the roots are different. So we have one single real root, so it is 1 into r raised to n. Okay, if there are many roots, it is C1 R1 raised to n. If there are two roots, then C1 R1 raised to n plus C2 R2 raised to n. Here we have only one root, so it is C1 R1. We needn't put R1 here because we have only one root. So C1 R raised to n is the homogeneous solution, isn't it? So now we have found out the value of R to be 1, isn't it? From this, we found that the value of r is 1. So we can substitute in this to get the homogeneous solution, that is C1 into 1 raised to n. Now C1 is a constant. We are not going to find this constant now. We will find it at the end. We are given initial solution A0 is equal to 1. From that, we will be able to find out the value of constant. At present, we are leaving it as such. We will find out the value of this constant at the end. Okay, so we have found out one part, that is homogeneous solution. Now, next step 2. What is step 2? What we are going to do in step 2? Step 1, I had found this part, that is the homogeneous part. There is a constant, I didn't find the value of it, but I'll find it at the end. Now, next part is particular solution. So, particular solution, we have to take the right hand side. For homogeneous, you took the left hand side. Particular solution, we have to take the right hand side. And looking at the right hand side, so step 2 is find particular solution. Find particular solution. So that is an of p. To identify from this an, distinguish this homogeneous and particular, we are writing h and p here. It is equal to, as I said, this polynomial, this question given is of degree 1, that is 2n, and the degree is 1. So we have to consider terms up till 1, that is d0 plus d1n. Okay, we have to take the polynomial terms up to n raised to 1. If there was n square, you should take up to n square. See, you have to take the first two terms, d0 plus d1n, because this power in the question, we have only up till n raised to 1. If you are given n raised to 2, you have to take the next term also. So since it is only up till n, we need to take only d0 plus d1n. And another case to be noted here, after writing this equation, what you have to do is look at the number of roots we had obtained. How many roots did we get here in a particular solution? In homogeneous solution, we had only a single root. R is equal to 1. There is only a single root, isn't it? This is a single root. So if we have only single root, then what we have to do is, after writing this equation, we have to multiply it by n raised to 1. That is n. So we had only, how many roots? This represents the number of roots. We have only one roots. So multiply this by n raised to 1. Okay, multiply by number of roots. multiplied by number of roots raised to the power n, multiplied by n raised to the number of roots, that is n raised to number of roots. I have only one root obtained here, r1, so I multiply it by n raised to 1, and that is n. Okay, so let it be equation 2. Is it clear? The given question, we can assume that it is equation 1, and the other is what we had obtained now is equation 2. So now how do we find? We are these d0, d1, etc. are constants. We have to find the value of these constants. Okay, so I had put an as d0 plus d1n into n. So look at the question. Here we have, or I'll write it once again. The question is an plus 1 minus an is equal to 2n plus 3. Okay, so we have written, by finding the particular solution, we have written an of p is equal to d0 plus d1n into n. We are multiplying by the number of roots, n raised to the number of roots. So, and I told you this is equation 2. This is our equation 1, which is the given question. Okay, this is our equation 1. This is the given relation, recurrence relation, given recurrence relation. Okay, so now we had this is the form of our particular solution. D0 plus, since there is only one, the degree of the polynomial on the right hand side is 1, we have to take D0 plus D1n, and this n is the multiplied, the entire term is polynomial is multiplied by n raised to the number of roots we had obtained for our particular, for our homogeneous solution. Now, see, look at this equation 1. I had written an. Now, what the next term I want is an plus 1. So, just substitute for n as n plus 1 in this equation 2. You will get an plus 1 of particular solution is equal to d0 plus d1, and instead of n, you can put n plus 1. The whole multiplied by n plus 1. So wherever n appears here, you can put n plus 1. Okay, that is, look at the right hand side of the equation. I want an and I want an plus 1. So I had written an. I found out an based on the equation that is already defined for this particular solution. That is d0 plus d1n, and then I multiplied this. I multiplied by looking at the number of roots I had obtained. So I got an. Then now I'm going to find out an plus 1. Just substitute n plus 1 in this equation 2. You will get an plus 1. Okay, if we solve this, if we expand this, you will get d0 plus d1n plus d1 into n plus 1. I'm just opening the inner this bracket. Then I'm going to multiply these two terms, that is d0 into n plus 1. So I'll get d0n plus d1n square plus d1n. So I have multiplied these three terms by n. Next I have to multiply these three terms with 1. So plus d0 plus d1n plus d1. So multiplying d0 with 1, I get d0, d1n with 1, I get d1n, and d1 with 1, I get d1. Isn't it? So, did you write this down? Did you write it down? Hello? So let it be equation 3. Okay. So I have found out an and an plus. Some of the terms will cancel, but I'm putting it as such. So I have found out an and an plus 1. Now I'm substituting it in equation 1. This an and an plus 1, I'm going to whatever I found here, an and an plus 1, I'm going to substitute in equation 1. That is, this 2 and 3 is substituted in equation 1. Substitute 2 and 3 in 1. substitute equation 2 and 3 in 1. So we will get, that is equation 1 is an plus 1 minus an is equal to 2n plus 3. This is equation 1. I'm going to substitute 2 and 3 in this equation. So an plus 1 is d1 n square plus 2 d1 n plus d0 n plus d0 plus d1 minus an. What we had obtained here, an is d0 plus d1 n into n. So that becomes minus d0 n plus d1 n square is equal to this term 2n plus 3. So what I did is I have found out the an and an plus 1. This is the formula that is defined for the polynomial. From there I found out an, then substituted for n is equal to n plus 1. I got an plus 1, this equation. I'm finding out an plus 1 because in the right hand side I have an and an plus 1. So this is the defined solution for an, and then in this equation I found I substituted n plus 1 for n, and I got this equation. So now and then I subtracted these two. I just substituted these two in equation 1, that is an plus 1. This equation is substituted here and this one I substituted here, and after substitution some of the terms will cancel off, and what we get is, see, this d0n plus d0n minus d0n gets cancelled. Then what is remaining? What is remaining here is 2d1n square plus 2d1n plus d0 plus d1. Isn't it? d1n square plus d1n square, it becomes 2d1n square. Then this 2d1n plus d1 plus d0 plus d1 is equal to 2n plus 3. Okay. Hope you are writing down with me. You are writing it down? Are you writing this down? Otherwise, you have to solve and see whether you are getting all these. Okay. Is it clear? So next step is very important. The next step. Okay. Once you get this solution, that is after substituting this and cancelling all terms, you get this form. Okay. And the next step, what we are going to do is, we are going to compare the terms on the left and right hand side. Okay, comparing terms on LHS and RHS. You are going to compare terms on the left hand side and right hand side. So when you compare the terms, you have n here, n raised to 1. So what is the coefficient of n raised to 1 on the left hand side? What is the coefficient of n raised to 1 on the left hand side? Similar powers should be compared. Here we don't have n square, so to compare, so we don't take that term. Next we have a term n, and here also we have a term n. So we can compare these two terms and equate the coefficients together. That is, here we have n raised to 1, here also this is n raised to 1 term. This is the coefficient of n raised to 1, this is the coefficient of n raised to 1 on the right hand side. So we can equate these two terms. You get 2d1 is equal to 2. Equating these two coefficients with similar degree on both sides, you get 2d1 is equal to 2. Here this 2d1 is equal to 2, or d1 is equal to 1. So we have found out the value of 1. Of d1. We have to find out d0 and d1. Okay. We have found out the value of d1. Next, what I'm going to do is I'm going to compare. So I had taken this term, I had compared its coefficient. What is remaining is the constant term. So I'm going to compare constant term with the constant terms on the right hand side. So the constant terms on the right hand side is d0 plus d1, isn't it? The constant terms on the left hand side is this. You have power of n, it is not present here. This we had already taken with the power of n has already been taken. The next, this is the constant term. Here we have the constant term as 3 on the RHS. So we just equate the constant terms on either side. You get 3. And we had found that we know that d1 is equal to 1. We have found that value earlier. So d0 plus 1 is equal to 3, or d0 is equal to 2. Okay, is it clear? So therefore we have found out the value of d0 and d1, and we know the particular solution is equal to d0 plus d1n into n. We started from this equation. This is a particular solution. This was equation 2. So we had found out these two values, and we can substitute it here. You get 2 plus 1n, 1 into n, isn't it? What is this? This is equal to 2n plus n square. Okay, so we have found out our particular solution. Is it clear? Is it clear? So let us go through it once again. So this is the general solution for a non-homogeneous equation. If the right hand side is a polynomial, you have to use this formula d0 plus d1n, etc. And here we are multiplying this by n, looking at the number of roots that we had obtained for the homogeneous solution. And we have obtained one root, and so we multiply this term with the power of n raised to the number of roots. And so you get an. Then we get an plus 1 by substituting n plus 1 in an. And with these two equations, we have found out an and an plus 1, substitute it in our main equation. And then we can find the values of d1 and d0 and d1 by comparing the terms on the left and right hand side. So here we have n as the n raised to 1 on here we have n raised to 1 on the right hand side, and its coefficient is 2. You can equate the coefficients of n raised to 1. You get the value of d1. Then when there is no n square term here to equate, so we don't take it. Then we have a constant term here 3. Equate it with the constant terms. You get d0 plus d1 is equal to 3. So, and d1 we have already found the value, so you get d0 is equal to 2. Now this is our general solution. This is a particular solution. Just substituting d0 and d1, we get the final particular solution. Now what is our general solution? We have found out only the particular solution. Now what is our general solution? General solution is an is equal to an homogeneous plus an particular. Okay, by adding these two solutions, we get the general solution for the recurrence, the non-homogeneous recurrence relation with a polynomial on the right hand side. So that is an is equal to, we had already found out the homogeneous solution an homogeneous solution, isn't it? Homogeneous solution. This is the homogeneous solution. Homogeneous solution, that is ANH is the homogeneous solution, that is C1 into 1 raised to n. 1 raised to n is 1. So you get homogeneous solution as C1. 1 raised to 1 is 1, any number is 1. So you get the homogeneous solution as C1 into 1 raised to 1. I'm not writing because it is 1 only. Then the particular solution which we have obtained now, what is the particular solution we obtained? 2n plus n square, or you can write it as n square plus 2n. Since polynomial we start with higher degree, we get n square plus 2n. Write in the order of decreasing degree. Okay. So you get C1 plus n square plus 2n. Now we have to find out the value of C1. So given A0 is equal to 1, we get put n is equal to 0. Put n is equal to 0 in this equation. In 3, you get A0 is equal to C1 plus 0 square plus 2 into 0. So A0 is equal to what? A0 is equal to C1. And so what is the value of C1? What is the value of C1? What is the value of C1? C1 is equal to 1 because A0 is 1. Very good. Type. This is given to us. A0 is 1, so C1 is equal to 1. So we have found out the value of this constant also. Now we can substitute in this equation 3 and we will get the final solution. We have to eliminate all constants. That's why we are solving it using the initial condition. So the final general solution for the given equation is, the final general solution for the given equation is C1 is 1. 1 plus 2n plus n square. 1 plus 2n plus n square, or n square plus 2n. Okay. So this is, what is 1 plus 2n plus n square? How can you reduce this formula? 1 plus 2n plus n square. What is the reduced formula for 1 plus 2n plus n square? Do you know the formula? What is the formula corresponding to this polynomial? 1 plus 2n plus n square. What is 1 plus 2n plus n square? N plus 1 the whole square. A plus b the whole square is a square, yes, a square plus 2ab plus b square. So a plus b the whole square, that is a square plus 2ab plus b square. So the general solution for the given recurrence, non-homogeneous recurrence relation, an is equal to n plus 1 the whole square. This is the answer. Okay. So you have to do 2 separate steps to reach the solution. So I'll give you an overview. So if the right hand side is a polynomial, what we have to do, isn't it? Given the right hand side is a polynomial, then we have to apply this equation for the particular solution. Homogeneous we know we can do separately as we had done earlier, but to find particular solution we apply this formula d0 plus d1n plus d2n square. Looking at the power, we have to select the number of terms in the particular solution. And after selecting, so we have found out the homogeneous solution. Here we have reached the homogeneous solution. Next step to find the particular solution, we are taking d0 plus d1n because the power is n. Given question is n raised to 1. Then what we have to do is we have to multiply this step. We have to remember we have to multiply these terms with n raised to the number of roots that we had obtained. We had only one root obtained when we calculated homogeneous solution. So you have to multiply it by n raised to 1. Then next step is we have to, we know an, then we have to find out an plus 1 because look at the equation. Now what we are going to do is we are going to compare the left hand side and right hand side. So you need an plus 1. So we found out according to this rule, an particular solution is d0 plus d1 n into n. So this is an. So this we got. Next we have to find out an plus 1 by substituting n plus 1 for n in this equation 2. So you get an plus 1. Just substitute n as n plus 1. You get this n becomes n plus 1. Here this n becomes n plus 1. Then you open the brackets, solve it, and you get an equation like this. Isn't it? Now we are going to substitute this 2 and 3 in equation 1. That is an plus 1 minus an. You are going to subtract these two. And after subtracting, we are going to compare the coefficients. So I substituted in this equation and I found that I got an equation like this. And here there's on the right hand side I have n raised to 1 term. I had equated the coefficients of n raised to 1. Also there is a constant term. I have equated the coefficients of the terms corresponding to constant terms on the LHS, and I found out the value of d0 and d1. They are all constants. They are all assumed values. We have to find out their values. So we had found out the values by equating the coefficients or by comparing the coefficients. So we had obtained this by comparing coefficients, okay, by comparing the coefficients on the LHS and RHS. Then After comparing, we found out the value of D1 and D0, and then we substituted in the particular solution and we got this as the particular solution. Then next, after finding the particular solution, I have to find out the total general solution. That is, it is homogeneous plus particular. And I found that homogeneous is C1, R1 raised to n. R1 was 1, so this becomes C1. Plus, particular solution is n square plus 2n. And now there is a constant term here, C1. To find out the value of C1, I can use the initial condition A0 is equal to 1. And then when A0 is equal to 1 means this is n, an. So the put n is equal to 0 in this equation 3, you will get A0 is equal to C1 and C1 is equal to, and given that A0 is equal to 1, you get C1 is equal to 1. Then once we have obtained all the values, we can substitute C1 in this is our general solution. So substitute C1 in this equation 3, you will get A1 is equal to 1 plus n square plus 2n or n square plus 2n plus 1. And that is the formula for n plus 1d, a plus b the whole square, or n plus 1 the whole square. So our general solution an is equal to n plus 1 the whole square. Is it clear to you? Is it clear to you? Did you understand the steps? Hello? Did you understand the steps? So that was case 2. That is when a polynomial appears on the right hand side. In the morning we saw when there is a constant term on the right hand side, what we have to do. The second case is a polynomial appears on the right hand side. Okay. Is it clear? So we have one more case, that is when an exponential term appears on the right hand side. That is the third case. Okay. So before that, let me tell you something.